current topic is half-life. What is a half-life? Half-life is the time it takes for half of the atom of the radioactive substance to decay. So let's clarify this concept. The terminology that we call the half-life, we noted by the capital T with the subscript 1 by 2. What actually this mean? So let's clarify this from a good example. Example is that suppose we have 20,000 atoms of a radioactive substance. That is the total quantity of a radioactive substance. I mean the number of atoms and a radioactive substance. So if we say that the half-life is 1 hour, so how many atoms of that substance will be left after? Let me say again, what is a half-life? Half-life is the time it takes for half the atom of a radioactive substance to decay. So a good example that we are considering here, that we suppose we had 20,000 atoms of a radioactive substance, and if we assume that the half-life is 1 hour, so how many atoms of that substance would be left after that? Let's put it like this. Uh, we have one lifetime that we consider 1 hour. So according to the definition of a half-life, so after the duration of 1 hour, the number of atoms that we will remaining in our radioactive substance will be equal to 10,000, and that 10,000 is equal to 50% of the total atoms that is we have in our samples. So if we say that the lifetime is 2 hours, so after 2 hours, how many atoms we will have in the samples? So that number of atoms will be equal to 5,000. 5,000, and that will be equal to 25% of the total quantity that we have initially assumed. That is 20,000. I mean, this 25% is not that of the 10,000. This 25% of the total is of the total quantity, total number of the atom that we say is 20,000 atoms. And if we proceed further and we say that the total lifetime, we say there's 3 hours, so the number of atoms after 3 lifetime will be equal to 2500, and that will be equal to 12.5% of the total number of the atoms that we have initially considered. So graphically, you can easily understand that initially at time t is equal to 0, we have this much of quantity of our sample. I mean, you can take that for a sample of the 20,000 atom as we have considered on the last slide. So after first lifetime, that is uh, n naught by 2, and at the time t is equal to t substrate half, 1 by half. This is the quantity that we leave after first lifetime. That is, we will have half of the quantity of the initial quantity. So after second half life, second lives, we will have the quantity that will remain will be equal to 1 by 4 of the initial quantity. And similarly, we say that after 3 lifetime, so after 3 lifetime, we will have 1 by 8 quantity of the initial substance. It's like you can see that we have reduced this quantity. I mean, it's a bigger one. I mean, differentiate circles, rectangle, and this is the triangle structures. So you see that how after a particular lifetimes the quantity is being reduced. So after, I mean, fourth lifetime, we have this minute quantity left. So this is a typical concept we have for the half-life. Uh, Again, some mathematics, some equations for the half-life. You know that in physics, we have to, I mean, to develop the concept, and that in order to have some clear concept about a particular topic. So we have to derive some basic equations. So what we have discussed on the previous slide, that is, let we consider a particular nuclei, and we say that F and not nuclei are present in that particular substance that we consider at time t is equal to 0, and one half of that number, that is n is equal to n naught by 2, have survived after a time t. So we can write then n is equal to n naught exponential minus lambda t. So according to our conditions, if n is equal to n naught by 2, so what we have to do, uh, we just need to put these equations, that is value of n, into these equations. So we will have n naught by 2 is equal to n naught exponential minus lambda, uh, this is the capital T for the half life. So you just rearrange these equations and take the natural log on the both side. I mean, what we do if you solve these equations, so what we will have, n naught will be cancelled with the n naught, 2 will be on this side, and you just take the natural log, so we will have these equations. So again, you just simplify these equations by multiplying both, by dividing both sides by lambda. So you will get the equation for the half life. That is half life, we denoted by the capital T with the subscript 1 by 2, and that is equal to half minus life, which is equal to natural log 2 divided by lambda, which is equal to, I mean, the value of this natural log 2 is equal to 0.693 divided by lambda. So what is this lambda? This is the basically the relation. This the capital T is, I mean, we represent the half life by this capital T with the subscript 1 by 2 is for the half life, and you say this is equal to 0.693 divided by lambda. So what is this lambda? This lambda we call a decay constant. So what is the decay constants? Let you have given the same amount, that is 1 kg of two radioactive materials with a half life of 10 hours and 50 hours respectively. So for first materials, after 10 hours, an amount of 500 gram will remain. But what for the second substance? I mean, if you consider the second substance, so for the second substance or for second materials, after 50 hours, an amount of 500 gram will remain. I mean, we are considering a very simple example. We are considering two different kind of materials with different half lives. One material we consider with the half life 10 hour, and the other material with a half life equal to 50 hour. So for the first material, we have that after 10 hour, the total quantity that we will left with equal to 500 gram. But for the second material, we say that the half life is quite larger, almost 5 times that of the first material. So for the second material, we say that after 50 hours, we will have an amount of 500 grams left. I mean, in order to have the same quantity of both the materials, so for the second material, we have to wait for 50 hours. That is, in order to decay of the same amount, the second material is taking longer. Why is taking longer? Because the half life is longer. It's 50 hours longer than 10 hours. So exactly, this factor is only depend on the half-life of the materials. Therefore, if any material have longer half-life, it will decay slower. I mean, the fact is quite obvious. I mean, the half-life is longer, so the decaying will be slower. So that we have seen here in this particular example. So this property is defined as the decay constant that we denoted by lambda, and we can derive this mathematically from the equation of the half life. I mean, we have the equation for the half life as we have discussed on the last slide. So from that particular relation, we can derive the equations for the decay constant lambda, which is given by lambda is equal to 0.693 divided by the half-life of that particular substance. So this is all we have for this lecture.